I'm Seth Weidman. I taught data science at Metis, a company that does data science boot camps and also does corporate training. So it teaches, it does these mini boot camps for companies of all different kinds, teaching their employees data science. And I actually just left Metis about a week ago, and I'm starting at Facebook in about a week. So, it is what it is. But I'm excited to give this talk. I love sort of speaking about this stuff. I think you hear a lot of buzzwords thrown around in data science and especially in deep learning. And I think it's really good to demystify them and actually show that they're a lot simpler than you might think. Cool. So this talk will be basically all about Ganz, starting from first principles, just talking about what are neural networks, and then expanding on that, talking about what are Gans, and then just kind of a hodgepodge of topics related to Gans after that, as you'll see. Let's get into it. So first, quick neural networks review, the sort of origin story of Gans. Then I'll show some Gans extensions and applications. And then I will talk about the future of Gans and of deep learning in general. I'll make this just a little bigger. How's that? Cool. All right, so what are Gans? So I don't know if the audio is going to work, but if you ever hear about Gans, you might feel like Homer Simpson does in this clip. Let me see if I can turn my sound on. Doesn't look like that's going to work. Internal speakers. If I turn this all the way up, will that work? All right, just listen carefully.
Hey.
Hold on. All right, I'll start it over.
Game? What's a game? Oh, a game.
So if you feel like that when you hear about Gans, this talk is for you. All right, so what are Gans? Gans stands for Generative Adversarial Network. And they're a method of training neural networks to generate images similar to those that the data that the neural network is trained on, and the training is done via an adversarial process. But what does all that mean? Oh, and first, just what are they? So basic Gans, sort of the early Gans could generate images from classic data sets like the MNIST digits data set. These are not actual digits written by a human. They were generated by a neural network. And Gans have gotten a lot better in the last sort of 4 years since they were invented. This is from about a year ago. It was cutting edge at one point. And these are not real people. These are generated by a neural network that had learned how to generate extremely high resolution images of people. This is from NVIDIA research, and we'll talk about this at the end. So why you should care? Jan LeCun, the director of AI research at Facebook on Quora, said, Gans and the variations now being proposed are the most interesting idea in the last 10 years in machine learning, in my opinion. Very cool. All right, but what are they actually? In fact, what are neural networks? So Gans are fundamentally neural networks. So let's review the essentials of what do we need to know about neural networks to understand Gans. So we've all seen diagrams like this when you're trying to understand neural networks. So they're like these circles and arrows that are connecting the circles, and there's these things called layers, and there's inputs and outputs. But what's really going on here? So there are many different ways of actually explaining what neural networks are. One way that gets a little mathematical, but that I think is essential to understanding them, is that they're really nested functions. So if there's inputs are x1, x2, and so on, then they're like f of g, of h, of whatever. They're nested functions of the inputs. They're universal function approximators, so if we nest these functions in the right way, we can in theory approximate any function, no matter how complex. And they're differentiable. Each one of these functions is differentiable, or at least not differentiable. At least the number of points where it's not differentiable is a very small number. So it doesn't matter. But they're differentiable functions. So what does that mean? That means you can basically think of it as a mathematical function that takes in a bunch of pixels, and it takes in some weight matrices that you might denote W, W11, and so on. And it does some operation to them. And this operation is something like you've seen in high school calculus. It's some continuous differentiable operation. It might be x11 squared times W1 plus W2, whatever. It's some operation that's continuous and differentiable. And every time we feed a set of inputs and weight through this network, we get a prediction. We call that P. We compare this prediction to the target, Y, And we get a loss vector, L, of the same sort of shape in terms of a multidimensional array as the predictions. And the loss is sort of the key thing. It tells us how much our network missed by. So we fed stuff through this differentiable function, and we got some quantity that tells us how much we missed by. And then we can train neural networks using the following procedure. Essentially, there are tons of variants on this, but they all boil down to feed a bunch of data points through the neural network, compute the loss, and then for every single weight in the network W, compute the partial derivative of the loss with respect to that weight. So increasing that weight increase or decrease my loss, and then continually just update your weights accordingly. So all the back propagation and matrix multiplications that happen in the course of actually computing the partial derivative of the loss with respect to all the weights, all that's doing is just getting everything to line up correctly so that we can actually update the weights in the right direction in every iteration. And then we update them according to this equation. And if you work it out, essentially this means if increasing a weight increases my loss, we decrease it. And if decreasing a weight increases my loss, then we increase it. This is sort of the standard gradient descent equation. In addition, though, and this is a key thing to understand for GANs, the differentiability of neural networks means we can also compute how much changing each of the input pixels would change the loss. Right? You can figure out, like, will changing this pixel make my neural network more likely or less likely to make a mistake? And this fact turns out to be what allows GANs to work. And it also turns out to be, if you've ever heard of adversarial examples, sort of examples that are tweaked a little bit and can trick neural networks, the reason those are a thing is because that you can compute essentially how much the loss of a neural network increases as you change the pixels and just keep changing the pixels in that way. All right, so that's the neural network foundation that we need. So how were GANs invented? What's their origin story? Well, it's really this guy plus beer. That's the high level. That's the TLDR. But what really happened, it's kind of interesting. So Ian Goodfellow was the inventor of GANs. He was then a grad student at the University of Montreal. And Yoshua Bengio was one of the leading researchers in neural networks in the world. And they were going to run a speech synthesis contest. And Yoshua Bengio, a side note on him that's interesting, is he was for a long time, and I think still is, the only sort of top 5, top 10 neural net researcher in the world that doesn't work at one of the leading tech companies. He's still at the University of Montreal full-time doing research. Okay, so they wanted to run a speech synthesis contest, and their idea was we'd have a discriminator network, so a neural network, that could listen to artificially generated speech and decide, is it real or is it not? They actually decided not to run the contest, concluding that people will actually just game the system by generating examples that will fool this particular network but don't actually sound like good speech. They'll just look at the network and figure out, okay, if I change my artificial speech by this much, can I just sort of game the system and fool this particular network? But then, as Ian Goodfellow tells the story, he was in a bar one night and he asked the question, can this be fixed by the discriminator network actually learning in addition? And this ultimately led him to develop GANs, which apparently he went home and coded up that night. So whether or not that's true, let's dive in and see what he did code. All right, so here's sort of, you might have seen that GANs can generate images that look like they're training data, but how do they actually work step by step? Let's get concrete. So first, you generate a random vector of data. All right, let's say length 100, Z1 to Z100. Then you feed this through some randomly initialized neural network to produce an output image that at first is just going to look like random noise. And we'll denote this matrix of pixels that we fed through this neural network X sub G for the generated. This is some fake image that we've generated. Then we feed this image through a second neural network. And this second neural network is designed to output a value between 0 and 1 that says, is this neural network, is this image real or not? All right, that's step 2. So what now? Okay, so we feed this fake image through a neural network, and we say, is the image real or not? So I think there's an interesting aside here. Are neural networks and GANs AI? Who says yes versus no? Who says no, they're not AI? Most of you don't have a strong opinion. I mean, to some extent, it's a little bit just semantics, but I think a better analogy is actually the following. They're more like dogs. We can sort of, there are these creatures and they each have their own characteristics, like just like different dog breeds are different, but we can sort of train them to do whatever we want. So once we have a neural network make predictions, we actually train it by saying, oh, no, when you get this input, you should output 0, versus when you get this input, you should output 1. That's actually, like, we as the researchers sort of train neural networks by deciding how exactly to reward them. And by deciding how to reward them, we make them do whatever we want. So what we do is we feed this fake image through the neural network. It outputs some prediction, and then we say, we want you, every time you get a fake image, to output 0. So we sort of tell the neural network that. And the neural network computes some penalty, just like the dog feels shame. It computes some penalty for making a prediction that was different than 0, and it uses that penalty to update its weight so that every time it gets a fake image, it will output 0. And it just gets better and better at every time it gets a fake image, outputting 0. And this network is called the discriminator. So it discriminates between real and fake images. Now, this is going to become important. We also compute, remember this network outputs values between 0 and 1. So we also compute the loss, the penalty if we wanted this network to output 1. So if we wanted the network to say that the image was real, we compute that penalty as well. We don't use that to train the network yet, but we compute that. Then we update the first network, the one that generated the image, with basically, we tell it generate images so that the loss with respect to the loss that this network produces when we tell it to output 1 is as low as possible. Basically, we tell the first network generate images that look real, that this network thinks are real. So we update, I'll get to that in one sec. So we update this first, we update the second network telling it we want it to output 0 every time you get a fake image. And we update the first network saying we want you to produce images that cause the second network to output 1. All right. So that's what that looks like. All right, and then finally, generate new random noise and just keep this process going and repeat. What's missing? Yeah, your real samples. We haven't actually given either of these networks any real images to work with. So this will get the generator very good at, it will get the generator very good at generating fake images, but it won't make the discriminator any smarter, because it will only be seeing fake images. So we just give the discriminator some real images, and we tell it, the discriminator is the second network, we just give it a bunch of real images. If we're trying to get it to generate images of cats, we give it images of cats, and it makes, just like before, it takes in an image, makes a prediction, we tell it, whenever you get a real image, we want you to produce a value of 1, and then it says, okay, I'll try to produce values of 1 when you give me a real image. We compute a loss, and then we update its weights so that every time it gets a real image, it produces something closer to a value of 1. And here's a description from the original paper on Ganz that sums it up really well. The generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the genuine articles. So those faces that we saw at first, they were generated basically using this process. And I think here's a cool thing. If you go on GitHub, this is actually, I'm presenting this from a Jupyter notebook, so all these links are in there. This is actually the original GitHub repo with Ian Goodfellow's code from May of 2014 that he posted, that is the first GAN ever. So like, I think that's pretty cool. All right. So that's the basic idea. There are lots of extensions of GANs. And one of the sort of, first of all, you had a question. I want to. Yeah. That's actually a really interesting point. I don't think anyone's ever asked that question. You could, in theory, Yeah, absolutely. Well, I'll just say this. Basically, his idea is you could get a really smart discriminator by doing the following. Give it randomly generated images, and repeatedly tell it to output 0 every time it gets a randomly generated fake image, and then give it real images and tell it to output 1 every time it gets a real image. In theory, you could do that. The goal of generative adversarial networks, though, is to get a really smart generator, right? You actually want to train a neural network that can take in random noise, any random noise in 100-dimensional space, and generate a realistic-looking image. So that's the actual goal. So that's a really good clarifying question. Cool. All right. So one of the, yes, sure. I think there's like a ton you could, his question is, could you talk more about how the weights actually get updated? And I think the key mental model that most people have when they think about neural networks is just that there are lots of different sort of tweaks on the ways to update the weights, but essentially you tell a neural network what you want it to output, and you tell it, update your weight so that when you get this input, you output that. Like, and in theory, it can just adjust its weight so that every time it gets this input, it produces that output. So yeah, I think that's like, there's a lot, we could go do a whole talk on that. So I'm going to go on, and I'll stick around for questions for as long as people want at the end. So a sort of simple extension of Ganz is just conditional Gans. So Ian Goodfellow did this coded this first version of Ganz and was able to generate images that looked like handwritten digits, right? So there's a famous data set, the MNIST data set, which has, a bunch of zeros, ones, twos, and so on, and he could generate images that looked realistic from that data set. The question is, what if you want to only generate zeros, or only generate ones, or only generate twos? How do you do that? So that's what conditional Gans do. So Gans can be modified slightly to generate images from a particular class. So how do you do that? It's actually pretty simple. You basically just feed a one-hot encoded vector representing whatever you're conditioning on, in this case, the particular digit, or you could do much more complicated things. You feed that into both the generator and the discriminator. So basically, step one, you have a network that instead of just taking in a random noise vector, your generator network takes in a random noise vector and some extra vector representing whatever you're conditioning on. So here it might be a vector saying, make sure this image is a 1. A one-hot encoded vector with 9 zeros and 1 1. Step two, you feed both of these through the discriminator. And again, we tell the discriminator output 0 when you get a fake image with this one-hot encoded vector. Then, as before, you use the loss you get to train the generator. So the generator is going to try to trick the discriminator and make it output 1 when it gets images that are generated by the generator. And then you ensure the discriminator gets smarter by giving it, for example, actual images of 1s and the one-hot encoded vectors, which represent 1s. And then and that's how conditional Gans work. So a lot of the really cool results involving Gans, some of them involve just generating generic faces in that example we saw at the beginning. But for a lot of really cutting edge examples, there's like, you want to generate an image of a cat or an image of a bird, and you want to do that by training on a massive data set that has just images of many, many different classes. The classic one is the ImageNet data set, which probably many of you have heard of, which has images of 1,000 different classes. So here's sort of an example from using conditional Gans to generate images from ImageNet of all these different classes from the conditioning on the class. So some of these are really remarkable and some of these are kind of creepy. So here's like, the ImageNet dataset has lots of different subspecies of animal. So here's like different images of the red shank bird. These are all generated by our neural network. None of these are actually real. And here's images of a St. Bernard. The cat images get really weird. I don't know what's going on there. So, I'm going to skip past those so you don't see nightmares. The Stonewall images are really interesting. They're all kind of like plausible stone walls, but clearly fake if you look really closely at them. Kind of like you could see how they could fool a computer kind of level images. And that's all just using conditional Gans. It's just using the GAN framework we just saw, but just conditioning on the class that you want to produce. And I'll also just show there's conditional GANs have been really recently used to do a ton of really advanced stuff. For example, you can people have taken, for example, in Google Maps. Google Maps, you can generate a lot of data where you have paired images of actual satellite images and actual and sort of Google Maps-y street view images like this, where it says output there. And from that, you can just train a conditional GAN to generate images that look like satellite images, conditioning on sort of the Google Maps-like input. And basically, you could make a drawing like, here they have a drawing like this that looks like a satellite image, and they output something that looks like a Google Maps, like a fake image that looks like Google Maps, like it came from Google Maps. And here's like, they inputted this and they outputted this. There's basically lots of really advanced examples of conditional GANs that are all just using this simple framework. For example, like this drawing generating this bag was just generate an image of a bag conditioned on this drawing here. So yeah, it all boils down to this simple sort of step-by-step procedure. All right, so there were a few papers that are sort of like big breakthroughs in GANs. And one of them was the DC GAN paper, the Deep Convolutional GAN paper. This is a paper that really exploded interest in this area and got a lot of people's attention. So there's a famous image from this paper with a bunch of bedrooms that were generated. So Ian Goodfellow, as you saw, generated these black and white images of handwritten digits, fairly simple. These are all fake images, 32 by 32 color images of bedrooms. And all of these are fake. They all sort of plausibly look like bedrooms. And this was published in like January of 2016. Oh yeah, that's the pix-to-pix thing. All right. So this paper was important for a couple of reasons. So it introduced a couple of concepts that pushed GANs forward, the sort of deep convolutional, deconvolutional architecture that I'll talk about a bit. And it used batch normalization, which was something that was introduced earlier, or basically 9 months before that paper came out. And it included some really famous visuals of the latent space that GANs produced, and I'll talk about that in a bit. And a really crazy fact about this paper is that the lead author was still in college when the paper was published. So that should make you all feel very bad. Yeah. And he's now a researcher at OpenAI. So, all right, so what's the idea of this latent space visualization thing? So what are GANs actually learning? Like, there's a question of, so GANs can take in a bunch of these vectors that you give it and generate things that look like realistic images. Okay, that's kind of cool. But are they just like, are they actually learning what it is to be a digit or a bedroom or something like that? Or are they just sort of doing some sort of tricks that allow them to generate a few images that look realistic? And one way to think about that is the space that they're sort of learning something that looks like the thing on the left, where, okay, they've learned that if you take in this vector, you can generate a bedroom. If you take in this vector, you can generate a bedroom. If you take in this vector, you can generate a bedroom. Or have they sort of learned how to map, if they learned a notion of bedrooms so that they can map any vector to something that plausibly looks like a realistic bedroom? That's sort of the question. And it turns out they showed in this paper for the first time that GANs are in fact learning something that is like an underlying notion of a bedroom. So here are 10 different images produced by their generative adversarial network. And the one on the left and the one on the right were produced by two different vectors. And you can imagine that they linearly interpolated between the vectors. They took 10 evenly spaced intervals between the vectors in a 100-dimensional space. And, they generated a bedroom from this vector, then from this vector, then from this vector, then from this vector, etc. And what's remarkable is that if you look at every single one of these images, every one of them looks plausibly like it could be a bedroom. In fact, there's even, in the one on the right, there's a huge window there. And in the one on the left, there's no window. And the window sort of appears out of this wall, and in every image it kind of looks realistic. So this is a big breakthrough, and it sort of showed that GANs are doing something like unsupervised learning, that they're actually learning a latent space of the training set images that they're being given. So the fact that they're learning a latent space was further proved by this a little bit creepy but very interesting and famous illustration of arithmetic in the latent space. So if you take the vectors of that produced images of smiling women and subtracted vectors that produced images of neutral women and added a vector that produced images of neutral men, you get images of smiling men. So it's sort of like it's learned an underlying notion of faces. And if you take, and you can do arithmetic on that. All right. How did they do it? So there's a couple sort of in the weeds tricks that they use, and I think that sort of pushed the field forward that nobody had done before this, and that sort of everybody uses since then. So one is they actually figured out how to get a deep convolutional and deconvolutional architecture working with GANs. So there had been deep convolutional neural networks before this, but nobody had figured out how to use GANs to generate images using a deep convolutional architecture. And so this is basically what their discriminator looked like, and this is sort of what their generator looked like. So essentially they had deep convolutional and deconvolutional architectures. Now, what are convolutions? Let's do a quick review of convolutions. So we've all seen diagrams like this in the context of convolutional neural networks, where there's like rectangles that have dotted lines connected to other rectangles, and there's some triangles, the pyramid-like things that are zooming in on the next rectangle and all that kind of stuff. This, by the way, some of you may know, is the architecture from the famous AlexNet paper. But what's really going on here? So what's really going on is for the most famous data set for images, the ImageNet data set, each image is 224 pixels by 224 pixels by 3, so 3 color channels, red, green, and blue. It's actually also interesting to note those images are extremely small. If you think about the images that your phone takes, they're like 2,000 by 1,000, right? So the fact that researchers can generate images that look like images from the ImageNet data set is not that impressive in the grand scheme of things, though they're getting there in recent years. But anyway, so what actually happens in these convolutions? If that's the image you start with, what does it mean to apply convolutions to that? Well, what happens in convolutions is these filters are sort of slid over images, and at each point there's a convolution operation that happens that sort of allows the filter to detect whether certain features are present at that point in the image. So it sort of looks like this. If the original image is blue, the convolutional filter is gray. That's the thing that the neural network's going to learn, and the output is this green thing here. I didn't make this, by the way. This is from the Theano documentation. Some of you may know. All right. So in practice, the neural network actually learns which filters to use. It learns filters that are useful to solve the problem it's been given. And what's interesting is you usually generalize the results of applying these filters. However, in the case of the ImageNet data set, in particular the AlexNet architecture, you can actually visualize the filters themselves. And I'll skip through the next couple things, but basically there's a bunch of filters that were applied to the first layer that were all 11 by 11. And there were 96 of these filters applied, but each filter had a red, green, and blue component. So you can sort of take all of those and smash them together and get a red, green, blue, a color image that shows you what filters the neural network learned were important feature detectors to actually figuring out what was in the ImageNet data set. And that gives you this famous visualization here, which sort of gives you a good intuition for convolutions. These are the filters that the AlexNet dataset learned were important to detecting what are in images. And if you look really closely at them, I don't even know if I can zoom in enough, these are actually 11 by 11 images. You can actually count the number of pixels. These are 11 by 11 images, and there's 96 of them. So these are like the 96 filters, each of which had a red, green, and blue component, where the red, green, and blue components are sort of smashed together to make one image. All right, so that's sort of they use deep convolutions, and that's what convolutions are. So the next, that should say batch normalization. Let's do it, why not? So the next trick is batch normalization. So batch normalization is an incredibly simple and powerful trick. It was introduced in two researchers from Google in March 2015 and quickly started being applied to like everything. The idea behind batch normalization is simple. So a regular neural network kind of looks like this. You have your input layer, your hidden layers, and your output layer. And we know empirically and sort of commonsensically that normalizing the input to a neural network helps with training. Basically, if you have one feature that's on a scale from like 0 to 1,000 and another feature that's on a scale from 0 to 1, then the neural network, before it starts adjusting its weights to figure out what the relationship between those features and the output is, it's going to have to figure out to adjust some of its weights to be on a scale 1,000 times smaller or 1,000 times larger than other weights. So we want to like make it easy for our neural network and normalize inputs when we pass data through. Turns out the same thing applies further down in a network. The same thing applies to this hidden layer 3. If we give it normalized inputs, then it will be easier for it to learn which of the inputs that it got are important to making its prediction. So how is it actually done? Well, sort of when you pass data through a neural network, usually do it in batches. You pass a batch of 64 images through at one time. And so each neuron, each sort of learned feature has some value, it's some number for each batch that you feed through the neural network. And so literally what you do if you have, 100 neurons, you take the 100 neurons, you subtract off their mean and divide by their standard deviation. So you get something with mean 0, standard deviation 1. In practice, there's actually an extra step involved, but that's basically the idea. That way, the thing you feed forward is an actually normalized quantity. There's one important caveat with this in convolutional neural networks specifically. It's sort of a technical detail, but if you think about what convolutional neural networks do, they actually they sort of learn groups of neurons. So what happens for example, a convolutional neural network that's learning to classify MNIST digits is it gets in a digit and then it applies 10 different filters, let's say. And what you get is 10 different versions of the original image, each of which has had a different filter passed over it. And so if you think about it, each one of these images is like 28 times 28. Each one of these images is 28 times 28 neurons. Each one of these pixels is an individual neuron. So if we normalized all of these, if we took all of these neurons and just normalized them together, then the actual images would sort of get messed up. The image would actually look different. So we don't want to do that. And this is sort of the point. If we don't want to do that. Instead, we want to sort of normalize within each image. So we want to modify all the pixels within each image by the same amount in each batch so that sort of the image doesn't get messed up. So that's a modification of batch normalization that you make for convolutional neural networks. All right, enough like theory in the weed stuff. Let's look at some cool results. So here's just like a hodgepodge of interesting results from GANs that I think are cool. By the way, are there any questions since we just got through the theory part? Yes, let's go over there.
What is the difference between the GAN and the image autoencoder that you train, and you just take a decode complete code and then predict the central code? Is it basically the same thing?
Yes. So his question is, what's the difference between GANs and autoencoders? They're accomplishing the same goal, which is to build a neural network that can generate images. They're just doing it different ways. I mean, we can talk about the details, but yeah, like autoencoders are doing it that way and GANs are doing it using this architecture.
Can you use an autoencoder to train your networks at the end and then just swap the order of events to create?
I'm not sure. I'm not sure. I haven't thought deeply about whether you could train an autoencoder at first and swap them. I don't know if anyone's tried that, but it's an interesting thought. We can talk more about that afterwards for sure. And then you've been raising your hand for a while. Yes. So if you gave, so his question is, yeah, I think the first question we'll maybe talk about afterwards. I'm not sure I completely followed, but the second question is an important one. I should clarify that. So your question was sort of if the generator is generating these fake images, then how does that relate to what the discriminator is doing? Is that fair? So I think what's one thing that's important to note, the images I was showing at first were showing in that step-by-step thing, we're showing that the generator is generating basically random noise. And what we ultimately want to do is we want the generator to get progressively better at generating images and the discriminator to at the same time be getting better at distinguishing between the images the generator is generating and the real images. So these two networks sort of have to get smarter in tandem. And yeah, so you're continually having the generator generate fake images and having the discriminator get both real and fake images. Yeah. There's actually an extra step there. I'll talk about that one maybe at the end if I have time. I see what you're saying. You're asking about the example here with the here. Yeah, there's actually an extra step involved there, so I'll talk about that at the end if I have time. That's a good question. Okay, cool. Let's talk about basically, yeah, we'll actually hit on that a little bit in this example. All right, so here's one cool application of these conditional GANs. This is pose-guided person image generation. And I think this paper sort of illustrates not only a cool application of GANs, but also how what's really required to do these well is large data sets and unique data sets that allow you to do certain things. So this paper sort of shows how you can synthesize images of people in arbitrary poses based on an image of that person and a pose. All right. So it's based on this data set called the Deep Fashion data set. And it's this data set of over 800,000 images, which are basically a bunch of images of different people wearing different kinds of clothing and with different labels of where all the people's like body parts are in the images and where the clothing lies. So to show an example, like this is an example from the paper from the data set. So like here's an example from the data set. So they'd have this image here and they'd have where all like the left elbow, left wrist, etc. of this woman are, and then where all the clothing parts are. And they have these cool visualizations here like of all the images in the data set where the left elbow was located in that image for all the images. So you can see in most images it's like on the left side, whereas the left sleeve was sort of located here. So for some images, their hands up like that. For some, it's down like that, and so on. And similarly over here for the right elbow and the right sleeve. So they had this data of people, and in addition, they had all of these labels of, how they were standing. And so from this, they could use a conditional GAN to say, given a condition of how we want someone to stand, generate an image that has this person standing in this pose. So like, here's an example. Here's a person, and here's the pose that the researchers wanted. So each of these points would have like a label, like left elbow, shoulder, head, whatever. And they'd use the GAN to generate this image here. And that's like an image of this woman sort of turned around. Now you can see that there's some weird features here, like her hands are missing and some other stuff. The straps on her dress are missing. But then they used another neural network, which is just a neural network to sharpen images. So to go from low resolution to high resolution images. And they produced this image sort of as their final answer for how they could generate images of people standing in arbitrary poses versus the ground truth. You can see that there's clearly some things off. For example, her straps are missing. But it's remarkable, like her hair is sort of on the right side. Like it was on this side in this image, and it was on sort of the correct side in the generated image, which I think is interesting. And this also works with sort of images of people just standing in real life scenarios. So here's a woman here, and we have this pose here of her like walking, and that's the image that was generated. It gets her shirt color right, everything. The sort of background looks plausible, versus sharpening that up gives you that. And the ground truth was that. So it looks like we also missed some details here. It looks like we missed her backpack strap. And maybe she has a bicycle. I'm not really sure. But yeah. So just one example, like another application of conditional Gans. It's kind of creepy, right? But it's also cool that the technology's advanced this far. All right. So another application of Gans that's become extremely hot, and I think is a decent candidate for like what the next big thing in deep learning might be, is semi-supervised learning. Who here has like heard of semi-supervised learning or is somewhat familiar with how it can be done with Gans? Okay, a lot of you. Cool. So semi-supervised learning even made it into Jeff Bezos's, what is no longer his most recent letter, but what was at one point his most recent letter to Amazon shareholders. So he says, in the US, UK, and Germany, we've improved Alexa's spoken language understanding by more than 25% over the last 12 months through enhancements in Alexa's machine learning components and the use of semi-supervised learning techniques. These semi-supervised learning techniques reduce the amount of labeled data needed to achieve the same accuracy improvement by 40 times. So, you know, when Jeff Bezos is announcing something, some machine learning breakthrough to Amazon shareholders, you know it's a big deal. All right, so what is semi-supervised learning? Really high level. It's sort of a third type of machine learning in addition to supervised and unsupervised learning. At a high level, the goal of supervised learning is to learn something from labeled data. Goal of unsupervised learning is to learn from unlabeled data. So semi-supervised learning asks, can you learn from a combination of both labeled and unlabeled data? And with Gans, the answer turns out to be yes. And the paper that introduced how to do this with Gans was a paper called Improved Techniques for Training Gans from a team at OpenAI in 2016. Very famous paper, introduced a couple of major ideas, one of which is semi-supervised learning and another of which I'll talk about later. All right, so how does it work? The basic idea is, let's say we're trying to build a neural network, just a simple classifier network to classify MNIST digits. The discriminator will output a probability vector of an image belonging to one of 10 classes, right? Some probability of the image being 0, some probability of it being 1, probability of it being 2, etc. Right? These will sum to 1, just be a probability vector. Then we'll compare these with the real values, turn this into a loss vector, and backpropagate. What do we do with semi-supervised learning? So with semi-supervised learning, we have a neural network that outputs two things. It outputs normalized probabilities of the digit being of the image that it gets. So the discriminator network outputs probabilities of the image being either a digit from 0 through 9 or a generated image. So it outputs basically a normalized probability vector over 11 classes. And in addition, it just outputs a number, which is the probability of the image being real. So it kind of looks something like this. P0 through P9 up to this probability of being a generated image, and then the probability of being a real image. And the probability of being 0 through the probability of being a generated image, these are normalized to sum to 1. So there's sort of like 11 classes the neural network is predicting instead of 10. And then you just separately predict, is it real or not? And then the data points are just then both real and fake images are fed through this classifier with the following labels. Real labeled examples are given labels simply of 0 for all the digits they are not, 1 for the digit they are, and 1 for being real, since they're real. And they're also given 0 for the probability of being a generated image, since they're not generated. Fake examples that are so the generator also generates fake examples, just like before. They're given labels of 0 across the board. Then they're given actually a 1 for the probability of being a generated image, and then a 0 for the probability of being real. And then, this is really the key with semi-supervised learning, we can learn from real unlabeled examples by telling the network, we don't know what digit these are, but they're not generated, and they are real. So that's sort of the key. And this allows the classifier to learn from real labeled examples as well as fake examples and real unlabeled examples. Now there's an issue that I'll talk about in a little bit, which is sort of a subtle issue, but there's this weird thing where the classifier is acting like both a discriminator and a classifier. It's at the same time trying to learn which digit is this And the same neural network parameters are trying to learn, is this a real image or not? So this like hybrid discriminator classifier is potentially problematic and introduces this interaction that they don't fully understand yet. And I'll get back to that in a second. And it turns out there's this trick that they use to make this approach work called feature matching. And the idea is this, and there's actually, they don't even fully understand why it works, but the idea is this. So the last layer of a convolutional neural network, before the values get fed into a fully connected layer, is a layer with many features that have been detected. So if you look at a diagram of a convolutional neural network, it's this layer here. It's like your last sort of vector of features. So for example, like in the convolutional neural, in the CNN architecture used in the DC GAN paper, the last layer was 2 by 2 by 128. So these are like 128 features of features of features of features that the neural network has learned. Then these are flattened into a single layer of 512 in this case. And then these 512 sort of features are used just as a classifier to try to figure out, is this image a 0, 1, 2, 3, or so on. So that's kind of what happens. This thing is then transformed into this vector here, and then tried to predict one of 10 outputs. So the idea that the authors used to sort of get semi-supervised learning with GANs is to train the generator not by just using the discriminator's prediction of whether the image was real or not, but to try to make it so the images the generator generated, this last vector of features looked the same as it did in real images. So whenever the discriminator got an image, for the fake images, this vector of features would look the same as the vector would look for real images. So they actually used the difference between these two vectors as the loss that they used to train the generator. Now, I think this is like very interesting and illustrates what is going on at the cutting edge of research. Even the authors of the paper don't fully understand why this works. So they say the approach in this paper introduces an interaction between G and the hybrid discriminator classifier that we do not fully understand yet. But empirically, we find that optimizing G using feature matching works very well for semi-supervised learning, while training G using GAN with mini-batch discrimination, so the traditional way, does not work at all. Here we present our empirical results using this approach. Developing a full theoretical understanding of the interaction using this approach is left for future work. So basically, they have no idea why this feature matching trick seems to work well for semi-supervised learning, but it does. And somebody else will figure out why. So this was, I'll just say the result and then I'll answer your question. Basically, this led to this was the first paper that showed that semi-supervised learning could work with GAN. So what did they actually show? There's this big data set called the Street View House Numbers data set. It's basically a much harder data set than MNIST. So they take images like this and try to figure out, is there a 651 in this image? Is there a 394 in this image? And so on. So they were able to accurately say which digit was in these images using only 1,000 labeled training images, which is pretty crazy. So they only had 1,000 labeled images, but this address number says 394, et cetera. They only had 1,000 labeled images, and they were able to get down to just 6% error using this semi-supervised learning approach because they had a ton of unlabeled real images in this case. They had a ton of images that Google had just taken and hadn't labeled of Street View house numbers. And the prior approach had a much higher error rate. And since then, and by the way, if you use the entire data set of 600,000 labeled images, you can get down to about 2% error, which is what Google actually uses in practice. But they figured out how to do 6% error with just 1,000 labeled images. So this all makes Jeff Bezos very happy. All right. You had a question, yes?
Yeah, in this setup, you were describing how there's 2 new outputs by the discriminator.
Yes.
9 to 10 classes, then there's probably a generated and probably real.
Yeah, I know. Shouldn't those be the same?
Yeah, aren't they the inverse of each other?
Well, actually, I'll just really quickly cover this. It seems like they should be, right? Basically, actually, it outputs 2 things. This vector of length 11 from P0 to Pgen, which is then normalized to sum to 1. That's one output. And then the probability that it's a real image is a separate output. And and the reason they do that is the key here is learning from real unlabeled images. So real unlabeled images are given 0 across the board because they're not zeros, they're not 1, they're not 2, whatever, nor are they generated images, but they are real. So that sort of separating out the probability of it being a generated image from the probability of it being a real image is what allows semi-supervised learning to work. But
Can we just go back to what the definition of real and generated? Are they not?
like the way I should have drawn this is there's a vector of length 11 that's separate from this other thing. Yeah. You're absolutely right. Like in theory they are the same, or they are inverses, but just when the neural network makes a prediction, it produces one vector of length 11 and then like a number between 0 and 1. And then that allows you to, train it.
So when it gives it an unlabeled image, it has all zeros in the first 11. And then it's supposed to pick the class, but not generate it.
That's right. So like when the discriminator gets a real unlabeled image, it's all it's doing is learning, right? It's just using it as training data. So it gets a real unlabeled image and it learns to produce zeros, it learns to produce whatever for these probabilities, but it learns to produce 1 for the probability of it being real. Does that make sense? Cool. Yes. Yeah. I mean, you can do that. You can do multiple losses with the neural network. Just sort of like, yeah. Exactly. Yeah, you have sort of 2 separate losses there. Okay. All right, so the sort of grand vision of GANs is to be able to generate photorealistic images conditioned on whatever you want. We're not quite there yet, though we may be soon. And where we are, though, is given a training set, we can generate extremely high-resolution images that look just like the training set. So this is sort of a famous example from NVIDIA research that came out in October of last year. And this is like what GANs generating images. There's a famous data set called the Celeb A data set. It's just images of celebrities from all around the world. And there are a bunch of 1024 by 1024 images. And this is what GANs learning how to generate images from that data set over 20 days looked like. And this one was I maybe skipped over that, but there was an article in the New York Times about this. It was like, this was when GANs hit the big time, was with progressive GANs. And I'll just briefly touch on like the main idea behind progressive GANs. This is like actually, this has since been improved upon, and it's sort of is specific to this particular thing. But basically what they did was kind of clever. They took these 1024 by 1024 images. They started out, as you can see, by training the GAN basically to just generate 4 by 4 versions of those images. So they way downsampled the images and just trained the GAN to generate a 4 by 4 version. Then they used the same weights and then updated the images to 8 by 8 images and used the GAN to generate 8 by 8 images from this data set. Then 16 by 16, then 32 by 32, all the way up to 1000 by 24 by 1024 images. And that's why it's called progressive growing of GANs. So that's sort of what that looks like. Going from 4 to 4 all the way up to 1000 by 24. There's since been GANs that have generated these high resolution images without using progressive growing. But this was sort of the big one. There's an interesting aside here though, which is how do we know these GANs are any good? Anybody, any ideas? Define good, exactly. How do you define good? I like that. So that's good. You could use Amazon Mechanical Turk or something and show people real images and fake images and say, do you think this is real? Do you think this is fake? And if you show 50-50 real and fake, they should think that 50% of the fake images are real, for example. Okay. What if you don't want to do that? Is there another way? So there's this is actually not an obvious thing if you start to think about it. We know that sort of the images generated by this progressive GAN look good. They look like faces, but how do we actually quantify that? And this is from Ian Goodfellow's tutorial at NIPS in 2016. He says, generative adversarial networks are generally regarded as producing the best samples compared to other generative methods such as autoencoders, but there's no good way to quantify this. So since then, people have come up with some interesting ways of quantifying this. And the most prominent of which is this thing called Inception Score, which is which I'll talk about now, and was also introduced in that same OpenAI paper, Improved Techniques for Training GANs. All right, so Inception Score, scoring GANs. So let's imagine we had a GAN that was intended to generate realistic images from one of a finite number of classes, such as MNIST digits. So realistic image that's either a 0, 1, 2, 3, 4, etc. So let's imagine that the generator generates a bunch of images. Generates 100 images. And then we feed those 100 images through a pre-trained neural network that has been trained to detect whether the image is a 0, whether it's a 1, whether it's a 2, whether it's a 3, or so on. And let's say for a given image we feed through the pre-trained neural network, which is really accurate, which knows whether to detect the image as a 0, 1, 2, 3, or so on. It produces this vector. It says, I think this image has a 10% chance of being a 1, 10% chance of being a 2, 10% chance of being a 3, etc. In other words, the pre-trained model has no idea which class this image should belong to. Do we think this GAN is any good? Yes? Who says yes? No, it's not. It should probably produce an image that this really smart network either thinks is a 0, or is a 1, or is a 2, or is an actual member of one of these classes. So if all else equal, if we see this, we conclude that this is not a very good generator. The way we formalize this is that the resulting vector here should have low entropy. So it should not have an even distribution over the class labels. So if you look at this vector, it should be instead 0.99. This image is definitely a 0, and then zeros everywhere else. So that's one component of Inception Score. Who can think of what the other component might be? Any other ideas? What's another? Think of how GANs could fail. So one way is you just produce crappy images. You produce images you're supposed to produce images of digits, and they don't actually look like a 1, a 2, a 3, or anything. What's another way a GAN could fail? Always the same image. Yes. So let's imagine every time it produced a perfect image of a 0. Well, that's okay, but we really want it to produce some zeros, some ones, some 2s, etc. So how would we quantify that? Any ideas?
It seems like this model would fail if the training database had image normalization applied to it prior to training.
Well, yeah. He said, what if the training data had image augmentation applied to it? I mean, if the training data was all zeros, then even if it was skewed, yeah, certainly GANs are just doing pattern matching. They're just trying to learn to generate things that look like the training data. So your training data has to be representative. So with this, we don't want the GAN to generate all zeros. So how could we sort of use this pre-trained network and get an idea and use similar reasoning here to figure out whether this GAN's any good? What do we want it to produce? So we don't want it to produce all zeros. That's a failure mode. What do we want it to produce? Even distribution. Exactly. We'd want it, if we generated 100 images, we'd want it to generate, if we fed those 100 images through the pre-trained network, we'd want the pre-trained network to say 10 of these are zeros, 10 of these are ones, 10 of these are twos, etc. We'd want it to be an even distribution over classes. So, let's say, for example, if you fed these 100 images through and you saw 91% of them were zeros, 1% were ones, 1% twos, etc., then that would not be a very good GAN either. So the way we formalize this is we want the vector of the frequency of the predictions over the classes to have high entropy. That is, we do want the classes here to be balanced. So these are the two components of Inception Score. And by the way, Inception just refers to the neural network architecture that's used to score these images. They use the Inception pre-trained model because it was the best model that was available at the time, but you could swap in any other model. And on the progressive GANs did indeed show a record Inception score on this famous data set called the CFAR-10 data set. It's a data set with a bunch of images from color images from 10 common classes, cars, planes, horses, stuff like that, just 10 classes. And progressive GANs did way better than anything else using Inception Score. And one other thing is we can't do this there's actually a lot of disagreement about how to do this. You can't do this in the Celeb A data set because there are no classes. There's not different classes in that data set.
Sorry.
Yes?
And this was still you still have an option that the generator creates an image that is very well predicted with high confidence, but the human eye is just noise.
Well, the Inception Score is trying to get at two things. A, are the images generated good? And sort of the first component of Inception Score says, are the images generated good? Because the hypothesis is if the images generated are bad, then the pre-trained model won't be able to figure out which class it belongs to. It won't be able to look at this image and be like, it's a horse, or it's a dog, or it's a plane. It'll just be like, this is gibberish, So in theory, that's the same thing as a human looking at the image and also thinking it's good.
So you don't think there's a scenario where an image that looks gibberish to the human looks like
There absolutely might be, yeah. So in theory, the GAN could have just learned how to generate images that can fool the Inception network but look bad to humans. But, that's unlikely, right? But it's true. That's theoretically possible. All right. Now, this actually doesn't really solve the problem of how do we know progressive GANs were good, because progressive GANs were on the Celeb A data set and there are no classes in that data set. So there's actually no real agreed upon answer to how do we figure out if these images are good, as opposed the Amazon Mechanical Turk approach of just ask humans, do they look realistic, is the best one. They use something called, they essentially randomly sample patches from the generated images and the real images. They randomly sample patches of different sizes and sort of score and sort of look at the similarity between these patches of different resolution between the two images to argue that their images generated were better than other ones. Essentially, and their logic here is that the really small patches sort of capture are the details between the two images the same, whereas the larger patches capture is the overall structure between the images the same. So that's sort of but there's no sort of agreed upon way to do this. So if anybody has an idea about how to really use some algorithm to figure out whether images generated are realistic where the data set doesn't have classes, that would be an open research area. All right, so I'll conclude with hypothesizing about what is the future of GANs and deep learning and stuff. So I think, what is the future of GANs? More generally, what is the future of deep learning? Can we predict it? So actually, I asked Ian Goodfellow in a LinkedIn message when progressive GANs came out if he was surprised by how quickly they were able to get to photorealistic image quality on 1000 by 24 by 1024 images. And his reply I thought was very revealing. His reply was, I'm actually surprised at how slow it's been. Back in 2015, I thought that getting to photorealistic video was mostly going to be an engineering effort of scaling the model up and training on more data. So I thought this was fascinating because if anybody should be able to predict how fast these advancements are likely to come, it should be this guy. So Ian Goodfellow's background, he is currently a staff research scientist at Google. He was the lead author on that Improved Techniques for Training GANs paper, and he knows how to scale models up. As an intern at Google, he was the one who took the massive Street View house numbers data set and figured out how to build a deep convolutional neural network on it that could take an image and figure out what the numbers in the image were, whether it was 394 or 151 or whatever. He did this in 4 months while he was an intern. So if anybody should know this, it's him, and yet still he was widely off. In 2015, he thought, oh, we'll have photorealistic video in no time, and just now we're starting to get to photorealistic images. And we're not even at photorealistic images that we can condition on things, which is really what you want. You really would like to be able to say, I want an image with this characteristic and this one, and it would just give you a completely photorealistic image of that. But instead, you sort of feed in a vector, and it produces an image that looks good, but isn't necessarily what you expected. And I think the fundamental thing going on here is that knowledge over time sort of looks like this. We might think that the experts like know everything and have all the answers, but the reality is that knowledge is like expanding really quickly. So even the experts might be like here, versus the people in this room are like here. The reality is in 5 years, people will be up here. They will know way more than the experts of today know. So the result of that is not even the experts of today really know where this stuff is going or how fast it's going to be going. So what is the future of GANs? Nobody knows. That's my conclusion. All right. Thanks, everybody. Appreciate it.